Hello and welcome back. This presentation will delve into more advanced concepts tailored for those curious to explore the intriguing landscape of quantum mechanics. Remember, don't forget to subscribe to our channel. More exciting subjects are on the way. The goal of TDPnet is to create a system where we can look at what's happening in real time and make changes to keep everything working smoothly. By following math principles, especially one called the least action principle, we can make sure the system runs as efficiently as possible, using the least amount of resources to get things done. The communication between service providers, SPs, A and B, utilizes bridges numbered 0, 1, and 2. The channel connecting them can be represented as a binary number of size 3, signifying a one-dimensional space of channels in the network. However, if each bridge corresponds to an entry point for a cluster, where each cluster is characterized by channels of equal bit length, this expands the representation into a two-dimensional space of channels. By recursively adding clusters at successive levels, the network can grow into an n-dimensional space, with the depth of dimensionality limited only by the system's resources and architectural design. This hierarchical structure allows for immense scalability and flexibility in channel allocation. A TDPnet data packet is structured as follows. Channel bits, 0 to 63. These 64 bits identify the channel through which the packet is routed, providing a unique channel ID for communication. Channel status bit, 1 bit, a single bit indicating the status of the channel, such as whether it is active or inactive. Layer bits, 8 bits. These 8 bits specify the layer of the network in which the packet is operating, helping to organize and manage hierarchical communication. Payload. The payload, appended at the end of the data packet, contains the actual data being transmitted. The payload is further characterized by type of data. Defined by the application designer, this indicates the nature of the data, such as text, binary, or multimedia. Status of data, also defined by the application designer, this describes the state of the data, such as whether it is complete, partial, or error-prone. This structure ensures efficient routing, clear organization, and flexibility in handling diverse application-specific requirements. Over time, at the endpoints of the channels, where the peered service providers, SPs, reside, the following process occurs to enable analysis. Incoming packets are accumulated until a desired threshold size is reached. Because the communication channel for a specific type of packet may vary, a measure is computed based on the binary number representing the channel's position r, which is normalized to a real number within the interval -1 to 1. Similarly, a measure is derived for the status s contained in the packet's payload. This leads to the definition of a TDPnet particle as SRT, where r represents the normalized channel position and t denotes time. This mathematical abstraction is used to perform calculations inspired by quantum mechanics principles, offering a unique way to analyze and model packet behavior within the network. It is important to emphasize that the state of a packet cannot be definitively measured until it is observed at the recipient endpoint. This mirrors a key concept from quantum mechanics, where the state becomes defined only upon observation. As previously mentioned, TDPnet analysis draws inspiration from principles of quantum mechanics, QM. However, we intentionally avoid certain elements of QM that we consider contentious or incompatible with our framework. Abstraction of spaces. We do not utilize the types of spaces typically employed in standard physics, as we believe these spaces do not necessarily represent a concrete reality. This reflects our perspective on the matter. Exclusion of imaginary numbers. In our framework, imaginary numbers are not treated as fundamental objects for mathematical manipulation. We hold that the physical universe is inherently finite, and any interval can be mapped to the real segment, 0, 1. While the use of imaginary numbers has proven remarkably successful in QM, we view it as an unintended but fortuitous artifact. Dynamic dimensionality. Instead of defining a fixed number of dimensions, we add dimensions as necessary, allowing flexibility to adapt to specific analysis requirements. To address these considerations, we adopt a distinct framework called Masuel Mechanics, short for Measurement Unified Energy Level. Masuel seeks to establish a connection between the quantities 1 and 2, where n is the number of bits in the payload. H dia x represents the entropy of the data packet at position x. The expression 2 results in a real number denoting the effort required to move x in the direction of y under the influence of the operator t. In this context, x and y are n-dimensional vectors with elements normalized to the interval -1 over n to 1 over n. T is an n-square matrix with entries similarly constrained to the same interval. The terms 1 and 2 serve as analogs to mass and force in classical mechanics, respectively. To measure the vectors, we compute the power series of their terms, resulting in values within the interval -1 to 1. This approach mirrors the methodology of classical physics, but here, vectors represent spaces of measurement precision. As dimensionality increases, precision improves, albeit at the cost of greater computational resources. Masuel Mechanics thus provides a robust framework for modeling and analysis while maintaining alignment with key principles of QM, albeit with adaptations to better suit our objectives. Thank you for making it this far. Masuel Mechanics represents our innovative approach to addressing complex challenges within TDPnet.